The last of the three I would call basic sorting algorithms is known as insertion sort. Again, this is a sorting algorithm that you might have encountered in a previous course. If you haven't, I certainly hope you enjoy this one, because I think that you'll come to discover that this was a little bit slicker, a little bit more clever perhaps in its approach than either bubble sort or selection sort, and there's a reward for this cleverness too, because it does actually generally perform a little bit better than bubble sort and selection sort. Okay, we saw bubble sort and selection sort. They both required that we take multiple passes through the array. The idea was during each pass through the array, a certain amount of work was done, and basically the ball was moved a little closer to the goalpost. Only after the last pass were we sure that the array was sorted. So insertion sort is a little bit different. Insertion sort pretty much just takes one pass through the array. We're only going to make a single pass through the array, but it's not quite as simple as that, because as we're making this pass through the array, we're going to do extra work to ensure that everything that's been encountered so far is sorted. Okay? So one pass and keep sorting, and then when we get to the end of that pass, we're going to be assured that the entire array is sorted. Okay, so how are we going to accomplish this task? So what is it that's going to allow us to maintain the entries in order up to a certain point as we make this pass through the array? Okay, well, the following reasoning pretty much is at the heart of pulling this off. Okay, we will imagine that we have all of the positions prior to position I sorted already, and we're examining now position I. So there's no telling how position I relates to everything before it, but at least we are assuming, or can assume, that everything prior to position I is already sorted. Okay? Well, the trick now is that we want to get everything up to and including position I sorted. Okay, so the trick is to look at the positions before I, but examine them from right to left. In other words, first look at position I minus 1, and then position I minus 2, then I minus 3, and so forth. And keep looking like that until you find an entry that is less than or equal to the entry in position I. Okay? Now the reasoning, and you have to pause and really see if you can't make sense of this, and if you have trouble seeing it right away, that's fine, because we're going to be running through a complete example in a moment. But the idea is, if we find a number, as soon as we find a number that is less than or equal to what's in position I, then we can deduce that the number in position I really belongs immediately after that number. Now, even if we discover where the number in position I should be placed, where does that number actually belong in the array once it's sorted, we still have the problem of making room for it, because there's already a number sitting there. And if we just copy the number from position I into the position that we've determined it belongs, If we're careless about this, we're going to lose that number. We're going to overwrite it, and we'll lose that data. So we have to instead be careful to take the number that's already in that position and shift it 1 unit right, 1 position to the right. Okay? But in doing so, we face a similar problem. There's already a number presumably in that position. And if we're reckless about this, we'll lose that number. We'll overwrite it. So we'll have to be careful to make sure that that number also gets shifted 1 unit to the right. And this is the basic thinking that underpins the whole business. We figure out where to put the entry in position I, but then we carefully, and I mean carefully, shift things so that the other numbers move into the positions where they belong, and we do that in the right way so as not to overwrite any information. And if you think about it, well, that means that the shifting 1 position to the right has to proceed in a right to left manner. And you're going to see this in a moment in the example, so I'm not going to dwell on it here. Okay, there's a possibility that we didn't mention yet. What happens if, while searching for a place to put the number in position I, what happens if we follow this procedure looking at the entries preceding that entry? And what if we discover that all of those entries are in fact greater than the entry at position I? Okay? Well, that's not hard. In that case, if all those numbers are bigger than what's in position I, then pretty clearly deduce that what's in position I really belongs at the beginning of the array. Okay? It should be in the first position of the array. And once again, to make room for it, all of the other entries before position I are going to have to get shifted 1 unit to the right. Okay, so if I've convinced you that there's an algorithmic approach to taking the already sorted array of numbers up to but not including position I, and then further sorting it to include position I. If you believe that, then of course we just repeat that. We just inductively repeat that so as to wind up with array sorted up to position I plus 1 and then I plus 2, and eventually when we get to the end of the array, the entire array will be sorted. Okay, here's the example. We're going to start with this black arrow on the second entry, basically saying, well, what precedes that, the portion of the array before that is certainly sorted already. Well, how come? Well, because the portion of the array before the second position just consists of 1 entry, which is 63, and of course there's only 1 number there, so of course that's sorted. Okay? All right, so now we want to start looking. Well, there's only 1 entry before 17, so we look at it and we discover that it's greater than 17. And since there's nothing else before 17, this corresponds to that situation where I said, well, what do you do if all the numbers before the number you're looking at are greater than the number you're looking at? And the answer is you got to shift all of those numbers 1 position to the right. Okay? And then that makes room to put the number you're looking at the beginning of the array. Okay, that may sound a little complicated, but the gist of it here is we have to shift the 63 1 position to the right and then copy the 17 into where it used to be. Effectively switch these 2 numbers. Okay? We have to be careful, of course, because if we just move the 63 into one position to the right, we're going to lose the 17. So actually, the very first step in this process is to take whatever number we're looking at, in this case 17, and copy it into a separate variable for safekeeping. And that then frees up, that then makes it safe to shift something into that position. Okay, so it's true that we're going to swap these two numbers, but I want you to think of it this way. We're going to take the 17, copy it into another variable for safekeeping, then we're going to shift the 63 one position to the right, and then we're going to copy from the place where we stored 17, we're going to copy that into position 0. But the effect, of course, is that those two get swapped. All right, then we continue forward and examine the next entry in the array, which is 92. Okay? We can assume that everything prior to 92 is already sorted, and it is. Okay? So now we look at the entry immediately before 92, right? So we're examining the third position right now. We got to go look at the second position. All right. The number there is 63. Well, that's less than the number 92. So this case is actually absolutely trivial. As soon as we see that, we deduce that the portion up to 92 positions, the first three positions, are already sorted. Okay, so there's nothing that has to be done there. So we continue. The next entry we're examining is 5. All right, the number that immediately precedes the 5 is 92. Well, that's greater than 5. So we need to look at the number that immediately precedes that, which is 63. That also is bigger than 5. So we need to look at the number preceding that, which is 17. That too is greater than 5. All three of these numbers are greater than 5. So this again is that situation where we deduce that the 5 has to get moved to the start of the array, and in order to do so, these other three entries are going to have to get shifted to the right. So the way this actually works is the 5 gets copied into a separate variable for safekeeping. The 92 gets shifted to the right from the third position to the fourth position, overwriting 5 there. And then the 63 gets shifted from the second position to the third position. And then the 17 gets shifted from the first position to the second position. Okay, now that we've shifted all three of those numbers to the right, we've freed up the location at the beginning of the array, and we simply take where we copy from the variable where we put the number 5, we copy from there to the first position. Okay, here it is again. Just like that. Okay, we don't actually see the shifting taking place in this visualization, but there it is. Okay, proceeding to the next entry in the array, 72. Right, so as we examine 72, we assume that everything before 72 has already been sorted, and it has. Okay, so now look at the entry immediately before 72, which is 92. That is greater than 72. So we have to go further back in the list. Okay, we have to examine 63. 63 is less than 72. So we infer that the 72 should come after the 63. But in order for the 72 to come after the 63, we're going to have to shift the 92 to the right to take the place of the 72. So the way it's going to work is, again, 72 gets copied to a separate variable. 92 gets shifted in place of 72. And then the contents of the separate variable get copied into the fourth position where 92 was. Okay? And voila, we now have the first 5 positions sorted. Okay, so we proceed to the last entry, examine 21, and we discover, okay, and then we look at the entry before 21, that's 92. Well, that's bigger than 21. We look at the entry before that, which is 72. That's also bigger. We look at the entry before that, which is 63. That too is bigger than 21. Look at the entry before that, we get 17. Okay, so we deduce that the 21 belongs after the 17. Okay? Just as it says here. Okay, in order to move the 21 into the position after 17, what we'll do is we'll copy the 21 into a separate variable. We'll shift the 92 to take the place of the 21. We'll shift the 72 to take the place of the 92. We'll shift the 63 to take the place of the 72. And then we'll copy the 21 out of that other variable and put it in place of the 63. Okay? And there it is. At long last, after we've made the entire pass through the array, we have a sorted array. So the array is sorted, but there are a couple technical issues that need to be addressed. And we've actually addressed at least some of these already. Well, we've talked about these things. When we do the shifting, we have to be careful not to overwrite entries that we would lose. Okay? So when we shifted to the right, we did so working from right to left, and that was important. Okay? And yeah, so generally we had to be careful not to overwrite anything. So here we go with the code for insertion sort. Okay, this has a nesting of loops, just like bubble sort and selection sort, but unlike those methods, the loops here are for different purpose. The outer loop is for the purpose of making a single pass through the entire array. Starting at position 1, which is, of course, the second position. So as we loop through the outer loop, I is going to represent, or I is, the position of the entry in array that we currently want to examine. Okay? The first thing we do inside that loop is to copy that entry into a temporary variable, as we were saying, for safekeeping, because we may wind up overwriting position I in the array. Okay? And then, yep, you guessed it, the inner loop, which uses j as its counter variable, is for the purpose of doing that backwards looking, beginning at position I. Well, anyway, j is going to start at I, and every time through the loop it's going to decrement, and what's going to be examined is position j minus 1. So j minus 1 is originally going to be I minus 1. The next time through, j minus 1 is going to be I minus 2. Next time through, it's going to be I minus 3. So that's that backward looking, starting just before position I, and looking at entries in the array prior to position I. And the loop continues, and this is then a little bit funny, so we have to think about this. It continues, the loop, as long as j does not become 0, as long as j stays greater than 0, and as long as the number stored in temp is less than the number stored in position j minus 1 of the array. So that last part there, of course, is basically saying as long as the number currently in position I, the number that we're currently considering in the scan, as long as that number is less than the number in position j minus 1, the number in the position during the backwards looking. Okay? As long as that's true, it keeps looping. And what it does while it loops is it simply copies from position j minus 1 to position j. And that right there is the right shifting. The shifting of entries from, in this case, from position j minus 1 to position j. Okay? So there you go. That loop will continue, 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 and there's only two things that will stop it. Either eventually you bump into an element that is less than or equal to what's in temp, or j becomes 0. If either of those events occur, then that inner loop terminates, after which whatever is stored in temp, which of course is the original value of array bracket I, and that original value of array bracket I then gets copied into the jth position, into position j of the array. Okay? Now, it may take you a moment. You may have to spend some time looking at this, but please do. Take some time. It's very short. Yes, it's quite slick, but it's a very serious piece of coding. And when you get down to the bottom line, you check it out, you're going to discover, if you take the pains to do it, that this does precisely what it was we were describing in the previous slides. These next couple slides basically repeat things that I said while we were looking at the code there, so I will just quietly present them to you. So as usual, I want to impress upon you the importance of actually studying the code. I feel like I've said this enough times, so I'll leave it at that. The course site also has a third-party animation of Insertion Sort that is really quite good. It's worth a look at. If you want to, you can examine how the code is written there. The author of that code organized things in a slightly different way, but the essence of the code is the same as what we're looking at here. Eventually, I certainly want you to download the C++ and Java sorting code, which does include insertion sort. You might think about doing that now if you haven't already done so. So when you're ready, go ahead and take the self-quiz on insertion sort. But I think, let's face it, I'm pretty sure you agree that insertion sort is a little trickier than bubble sort and selection sort. So I want to encourage you to, take the extra time to make sure you really appreciate the details of insertion sort, and particularly sweat the details of the code. You really ought to spend some time making sure you understand the code before you go on and take the self-quiz. Okay.